I want you to imagine the universe just minutes after the Big Bang.
Oh, wow, right back to the very beginning.
Yeah, exactly. The very beginning. There are no stars, no galaxies, no planets, nothing like that. It's just this unimaginably vast, chaotic, and rapidly cooling soup of subatomic particles. Space is dark, it's violently expanding, and then as the temperature drops just enough, something really profound happens.
Right, the particles finally slow down.
Exactly. Out of all that absolute chaos, those scattered particles find each other, they slow down, they attract, and they just sort of click together to form the very first, most abundant piece of matter in existence, the Genesis atom. I'm talking about hydrogen.
You know, when you look at that specific moment in cosmic history, you are literally looking at the foundational blueprint for, well, everything else. Hydrogen isn't just some element sitting quietly on a periodic chart in a high school chemistry classroom.
Right.
It is the fundamental architect of the cosmos. Like every structure we see in the night sky began right there in that exact moment.
And that is the mission of today's deep dive. We're taking a journey through our source material today to look at the complete epic story of element number one. We really want to understand how this singular, beautifully simple building block went from forming the very first galaxies in the early universe to becoming the biological lifeblood of Earth.
Yeah, and why it might hold the ultimate key to our clean energy future, too.
Exactly. It's just wild.
It is the ultimate origin story because, every other element that makes up the device you are listening to this on, or the earth beneath our feet, the iron in your blood, all of it owes its existence down the line to what hydrogen started in those early cosmic moments.
Okay, let's unpack this, because I want to go back to that early universe. After that initial cooling, space is mostly empty, right? It's dark. But it is filled with these unimaginably large clouds of hydrogen gas stretching across millions of light years.
Or it's just massive diffuse clouds.
And for a long time, nothing much happens. But then gravity goes to work. Gravity begins pulling these massive clouds together, drawing them tighter and tighter. So we move from the cold vastness of empty space straight into the immense crushing core of a newborn star. And gravity is basically acting like a massive cosmic pressure cooker.
But I have a fundamental question about the physics here.
Sure. What is it?
Well, since hydrogen nuclei are positively charged, shouldn't they naturally repel each other, like pushing the two positive ends of a magnet together?
Yeah.
How does the universe force them to actually combine?
That is a great question. And what's fascinating here is that the universe solves that problem using sheer brute force to overcome the electromagnetic force.
Brute force.
Yeah, exactly. Because under normal circumstances, you're completely correct. Protons will just bounce off each other long before they ever touch. But gravity, in these massive early clouds, it just doesn't take no for an answer.
As it pulls all this hydrogen gas inward, the pressure at the center becomes, incomprehensibly high. And as the pressure rises, the temperature skyrockets into the millions of degrees.
So it creates a stellar furnace, essentially.
Exactly. And the heat makes these hydrogen atoms move at blistering, frantic speeds. They are zipping around so fast and they're packed together so tightly by the crushing weight of the star's outer layers that they simply cannot avoid each other anymore.
They just have nowhere else to go.
Right. The extreme speed and pressure finally overpower that natural magnetic repulsion. The protons are slammed together with such unimaginable force that they fuse. They merge to become a brand new element, which is helium. And, this is the process of nuclear fusion.
And that fusion process produces a pretty massive byproduct, right?
Oh, absolutely. When those hydrogen atoms fuse into helium, a tiny fraction of their mass is converted directly into pure radiant energy.
Wait, literally just mass turning into energy?
Yes, exactly. E equals mc squared in action. That energy pushes outward against the crushing force of gravity, and it creates a perfect equilibrium. A star is born. Those hydrogen atoms violently smashing together release the tremendous energy that powers our sun and, well, nearly every single star you see in the night sky.
It's just crazy to think about. Every ray of sunlight that hits your face, every photon that warms our planet and drives our weather systems is the direct result of hydrogen atoms being crushed together millions of miles away.
It really is.
But here's where it gets really interesting, because to understand how hydrogen possesses this cosmic power, We have to zoom all the way in. We need to transition from the macro scale of blazing stars right down to the micro scale of the atom itself, because the immense power of hydrogen actually comes from its minimalist design.
Yeah, its structure is so basic.
Right. If you think of atoms like architecture, hydrogen is the absolute minimalist architecture of the universe. It is just a core, a single proton, and a single electron orbiting it. One proton, one electron. No inner shells, no complicated layers. It is completely unlike any other element on the periodic table.
And that simplicity is its superpower. Because there's no bulky inner shell of electrons in the way, that single electron is highly exposed, and the proton at the center is very accessible. It makes hydrogen incredibly versatile as a chemical builder.
Right. And that minimal structure defines the vast majority of hydrogen out there, a form we call protium. But I know from our sources that the universe occasionally modifies that foundation.
Right, it throws a curveball.
Exactly. Sometimes a neutron gets added to the nucleus. It's still hydrogen because it still has one proton, but it's heavier. This isotope is called deuterium. And then if you add another neutron, you get tritium, which is even heavier and actually radioactive.
Yeah.
And scientists use these specific heavier isotopes for advanced fusion research on Earth. But I guess my question is, why don't we just use regular, simple hydrogen like the sun does?
If we connect this to the bigger picture, it's because we don't have the luxury of the sun's immense gravity to force fusion to happen. We don't have a cosmic pressure cooker. We have to replicate that process in laboratories using, heat and magnetic fields.
Which is incredibly hard to do.
Incredibly hard.
Yeah.
So we need an advantage, and those extra neutrons provide it. Neutrons don't have an electrical charge, but they do exert the strong nuclear force. Think of it as atomic glue.
Okay, atomic glue. I like that.
Yeah, so when you smash a deuterium atom and a tritium atom together, those extra neutrons provide enough of that strong nuclear pull to help the nuclei stick together at temperatures we can actually achieve on Earth.
Oh, wow. So it's basically an atomic shortcut.
Exactly.
And those heavier isotopes play a massive role in standard nuclear fission reactors too, don't they? I mean, when you make water using deuterium instead of normal protium, you get heavy water.
Yes, heavy water. And heavy water solves a critical problem in a fission reactor. In fission, you are splitting uranium atoms, which releases neutrons that go on to split other uranium atoms, creating a chain reaction.
Right.
But those newly released neutrons are moving way too fast to reliably hit another uranium target. They need to be slowed down.
So why not just use regular water?
Well, if you use normal water to slow them down, the protium atoms, the regular hydrogen, they tend to just absorb the fast-moving neutrons, which is bad because that can stall the entire reactor.
Oh, I see.
But deuterium, on the other hand, already has a neutron. Its nucleus is full. So when a fast neutron hits heavy water, it bounces off, losing speed without getting absorbed.
Like a bumper car.
Exactly like a bumper car. It slows the neutron down to the perfect speed to safely sustain the nuclear chain reaction.
That is wild. We've spent all this time talking about hydrogen as this untamable force of nature crushing itself in the cores of stars, fueling nuclear reactors. But the ultimate irony is that this same blazing, volatile element is entirely responsible for the life-giving, cooling liquid of water on our planet.
Yeah, it really is a paradox.
It creates the fire, but it also creates the water to put it out.
That's a great way to put it. When two hydrogen atoms bond with one oxygen atom, you get H2O. And the way hydrogen behaves in that molecule dictates the rules for biology on Earth.
How so?
Well, the oxygen atom is larger and hungrier for electrons. It pulls the single electron from each of the two hydrogen atoms closer to itself. And this leaves the hydrogen ends of the water molecule slightly positively charged, and the oxygen end slightly negative.
Well, it creates a tiny magnet.
Right. And water molecules are constantly sticking to each other, positive to negative, in a massive microscopic pile of magnets.
And we call those hydrogen bonds, right?
We do. And they give water its incredibly high surface tension. They allow water to travel upward against gravity in the roots of a giant redwood tree. But most importantly, they dictate why ice floats.
Which is huge. If ice didn't float, we probably wouldn't be having this conversation right now. Because in almost every other substance in the universe, the solid form is denser than the liquid form, so it sinks.
Exactly. But because of the specific geometry of those hydrogen bonds, when water cools down and freezes, the molecules are forced to push apart into a rigid, open lattice structure. The ice actually takes up more physical space than the liquid.
It expands.
It expands, becomes less dense. If water behaved like normal liquids, our oceans would have frozen from the bottom up during the first ice age.
Oh, wow.
Yeah, it would have killed all marine life and turned Earth into permanently frozen rock. Hydrogen bonds prevent that.
That's incredible. But I actually want to offer a bit of pushback here on how we talk about life. When we discuss biology, we tend to frame oxygen or carbon as the ultimate life elements.
Yep.
We breathe oxygen. All of organic chemistry is built around carbon scaffolding. But looking closely at the mechanics of our biology in this source material, isn't hydrogen doing the actual heavy lifting?
I would absolutely agree with that. Carbon is the scaffolding, but hydrogen is the mortar holding the bricks together. Because of that single exposed electron we talked about earlier, hydrogen is incredibly eager to bond.
Right.
It caps off the ends of carbon chains. Without it, you couldn't have proteins, fats, or carbohydrates.
It even holds our genetic code together, doesn't it?
Yes. The famous double helix of our DNA, those two twisting strands of genetic information, they are zipped together right down the middle by hydrogen bonds.
It's just microscopic magnets holding our blueprints together.
Exactly. Those bonds are strong enough to hold the DNA together securely so your genetic code doesn't fall apart. But they're also weak enough that they can be easily broken and unzipped when a cell needs to divide and replicate its DNA.
Which is essential.
Essential. If those bonds were made of stronger, more permanent covalent links, the fundamental mechanism of cellular reproduction would just grind to a halt. Life requires an element that can hold on tight, but also let go when necessary. Hydrogen is perfectly engineered for that job.
It's so cool. This one simple element builds the stars, it fills the oceans, and literally zips our DNA together. And then humans looked at this wild foundational element and thought, let's put it in a tank and harness it.
Yeah, we're pretty ambitious.
We really are. Mastering hydrogen could be the greatest industrial achievement of our species. I mean, we started harnessing it when we needed a tremendous amount of concentrated energy, like, leaving the planet entirely.
Yeah, the Apollo missions were a prime example of that. When humanity stepped onto the moon, we did do it with gasoline.
Definitely, yeah.
You take liquid hydrogen, you combine it with liquid oxygen, and you add a spark. They combust with incredible ferocity. The chemical energy released by that reaction provided the immense physical thrust to push the Saturn V rocket out of Earth's gravity well.
And the craziest part is the exhaust, right?
Yeah, the only exhaust from that massive fiery explosion was pure water vapor.
That is wild. And that leads perfectly into the modern holy grail of clean energy, the fuel cell. Because a fuel cell takes that exact same concept, combining hydrogen and oxygen, but instead of using a massive explosion to launch a rocket, it does it elegantly, quietly, to generate electricity. I really want to break down exactly how it pulls electricity out of this reaction.
Sure, so in a fuel cell, you feed hydrogen gas into one side and oxygen from the air into the other. But before the hydrogen can get to the oxygen, it has to pass through a barrier called a proton exchange membrane, or PM.
Okay, PM.
Think of the PM as an atomic bouncer. It is chemically designed to only allow positively charged protons to pass through it.
So as the hydrogen atom hits the membrane, its single electron is basically stripped away and blocked.
Exactly. The proton slips through the membrane to go meet the oxygen, but the electron still desperately wants to reunite with its proton.
It's attracted to it.
Right. But since it can't go through the membrane, it is forced to take a detour through an external wire to get to the other side.
And electrons moving through a wire.
Is the literal definition of electricity.
Oh.
We harness that flow of electrons to power a car's electric motor, a building, or, a laptop. And once the electron completes its circuit, it rejoins the proton and the oxygen on the other side.
And the exhaust.
The only byproduct dropping out of the tailpipe is H2O, pure drinkable water.
So what does this all mean, like for the listener sitting in traffic right now, or for the future of global energy consumption? We have a completely clean energy source. No carbon emissions, no smog. We could decarbonize heavy industry, shipping, aviation sectors where heavy lithium-ion batteries just don't scale.
Exactly. Hydrogen could act as a massive clean battery for the entire planet. Imagine excess solar and wind power generated during the day being used to split regular water into hydrogen and oxygen.
Right, so we make our own hydrogen.
Yeah. We store the hydrogen. And then at night, when the sun is down and the wind stops, we run that hydrogen back through fuel cells to power our cities. We unlock the universe's primary energy currency.
Sounds perfect.
But this ambition comes with massive physical hurdles.
There is always a catch. If this element is the most abundant thing in the universe, and its exhaust is literally just water, Why aren't we all driving hydrogen cars and living in hydrogen-powered houses right now?
Well, the very properties that make it so unique, the things that make it the smallest and lightest element in existence, make it maddeningly difficult to control.
It is the ultimate escape artist. Storing hydrogen is like trying to keep a swarm of microscopic bees in a cardboard box. It inherently wants to escape any container we build for it.
That's a perfect analogy.
Because the atom is impossibly small, hydrogen gas can slip right through the atomic structure of solid steel tanks, can it?
It can. It causes a phenomenon known as hydrogen embrittlement. Over time, those tiny atoms weave themselves into the metal of their containers and pipelines. They wedge between the metal atoms, expanding microscopic cracks, making the steel brittle and prone to shattering.
Yikes. So we can't just repurpose old infrastructure.
No, you can't just pump it through our existing natural gas pipelines without major safety risks. You have to build entirely new infrastructure with specialized materials.
And even if you build a specialized container, getting enough hydrogen into the tank to be useful is a nightmare of physics.
Hmm.
Because it's so incredibly light, a tank full of hydrogen gas at normal pressure barely contains any actual energy.
Right. To get enough energy density to power, say, an ocean freighter across the Atlantic, you have to pack a lot of it into a very small space. And the first way to do that is extreme pressure. We were talking about compressing the gas to 10,000 pounds per square inch.
That's insane.
It requires incredibly strong, heavy, and expensive carbon fiber tanks.
Okay, so that's pressure. The second way is turning it into a liquid, which is what NASA did.
Right. But hydrogen does not want to be a liquid. To force it into a liquid state, you have to chill it down to minus 253 degrees Celsius.
Minus 253.
Yeah, that is just a few degrees above absolute zero, the coldest temperature theoretically possible. The sheer amount of energy it takes to cool the hydrogen down that much, and the complex vacuum-insulated tanks required to keep it from boiling off immediately are immense engineering hurdles.
This raises an important question, though. Are these hurdles insurmountable, or are we developing technological breakthroughs to bypass the extreme cold and extreme pressure?
We are definitely developing breakthroughs. Material scientists are working on new technologies called metal organic frameworks, or MOFs.
MOFs, what do those do?
They act like microscopic sponges. At an atomic level, they are highly porous, cage-like structures. And instead of using brute force like high pressure or freezing cold, MOFs use chemical attraction.
Wait, how does it work?
They use subtle electrostatic forces called van der Waals forces to draw hydrogen molecules into their tiny pores and trap them safely at near room temperature.
That's brilliant.
And when you need the energy, you just apply a little heat, and the sponge releases the hydrogen into your fuel cell. Mastering these storage innovations isn't just another engineering challenge, it is the absolute prerequisite for the world's future energy systems.
Wow. You know, we've taken an incredible journey today tracking the epic story of element number 1. We started in a chaotic, cooling universe just minutes after the Big Bang, where hydrogen became the very first matter to form.
Right?
We watched gravity compress it into the nuclear furnaces of the very first stars, lighting up the darkness of space. We zoomed in to see its beautifully minimalist atomic structure, how it tethers the molecules of water together, making the oceans hospitable, and how it zips the DNA in our bodies into that iconic double helix.
It's done a lot of work.
It really has. And finally, we explored how humanity is desperately trying to bottle this cosmic force to blast rockets to the moon and potentially power a completely clean, decarbonized future right here on Earth.
And, every single time you step outside and look up at the stars on a clear night, or even just when you walk into your kitchen and take a sip from a glass of water, you are directly, physically interacting with the very first matter that ever existed in the universe.
That's wild to think about.
It has survived billions of years, moving from the void of space into the biology of your own body. As humanity looks toward deep space exploration, the profound question remains, will the oldest element in the universe be the exact technology that propels us into our deep future?
Definitely something to mull over the next time you look up at a starry sky. Until next time, thanks for joining us on this deep dive.